Thanks. It's very nice to have the opportunity to give the talk, especially during the summer when so little is happening. I should say that the talk is slightly experimental. It's my first online talk. So anyway, I'll be trying to write on the tablet and speak through the camera. But if the text becomes illegible or something, please let me know. Or yeah, please also interrupt me with questions. It's kind of hard to get a sense of whether or not people are following well with the digital format, so please do feel free to interrupt me. So we've heard several talks in this series of seminars on canonical metrics, on Kähler manifolds. So in particular, things like Kähler-Einstein metrics, constant scalar curvature metrics, extremal metrics. And also in the last couple of weeks, we had a talk on case stability as well by Chen Yang and Buxon as well. And what I'll be talking about is kind of a variant of that story that makes sense in a different geometric situation, namely on holomorphic submersions rather than Kähler manifolds themselves. So before turning to holomorphic submersions, what I'd like to talk about is just the usual story on smooth projective varieties for a few minutes before turning to the new material. This will be just kind of a reminder of the importance and of what the strongest kind of results are about constant scalar curvature metrics and case stability. So we'll let X be a projective complex manifold. So if you're more of an algebraic geometer, you could think of X instead as a smooth projective variety over the complex numbers. And we'll take an ample line bundle on X. So let L be an ample line bundle on X. And again, from a more differential geometry perspective, you could take C1 of L to be a Kähler class instead. So, or C1 of L, a Kähler class. So by the Kähler embedding theorem, these are really equivalent hypotheses, ampleness and Kählerness. So I'll call then the pair X, so the smooth projective variety together with an ample line bundle, I'll call this a polarized manifold. So then the motivating question that's really at the start of the whole field is the following question, which became prominent really, I think, in the general case, mostly in the 80s. So is there a canonical or most natural choice of Kähler metric in this Kähler class that we have? Okay, so we have this Kähler metric. It has some infinite dimensional family of, Kähler class, and it has an infinite dimensional family of Kähler metrics. And you can ask, is there a choice that best represents the geometry of the complex manifold? So is there some kind of canonical way to choose a Kähler metric in this Kähler class? The question is quite vague as it's stated, because I haven't really told you what properties I would want. And it was really Calabi who gave the first proposed answer. So Calabi proposed that one should look really at extremal Kähler metrics, which are even more general, but I'll focus on constant scalar curvature metrics because they'll be the important thing for today, and they're the most prominent class of canonical Kähler metrics. So Calabi proposed that constant scalar curvature Kähler, and given how long it takes to write down, I'll abbreviate this to cscK. So Calabi proposed that cscK metrics are the right choice. Okay, so the constant scalar curvature condition really does just mean that the scalar curvature of the associated Riemannian metric is constant, but in Kähler geometry, there are these nice formulae for the Ricci curvature and the scalar curvature, which I'll remind us of. So first of all, the Ricci curvature is just given as minus I del bar log of omega to the n. So you think of here, omega is inducing a Hermitian metric on the tangent bundle. So omega to the n induces a Hermitian metric on the top exterior power of the tangent bundle, which is minus kx. And this is just the curvature of that Hermitian metric. So in particular, for free, you get that the Ricci curvature is in the first term class of the manifolds, which by definition is the first term class of the anti-canonical line bundle. So this is the Ricci curvature. And the scalar curvature is just the contraction of the Ricci curvature. So scalar curvature times omega to the n is equal to n reach omega wedge omega to the n minus 1. So here n is equal to the dimension of x. So again, these are really the standard quantities associated to the Riemannian metric in Riemannian geometry. But given how nice these formulae, I thought it worth writing them down. One thing that comes from the second formula for the scalar curvature and the fact that the Ricci curvature lives in the first term class of the manifold is that if you have a constant scalar curvature Kähler metric, then the scalar curvature has to be a topological constant. So one sees just from this, first of all, that the integral over x of s of omega to the n is equal to n times the integral over x of c1 of l to the n minus 1 dot c1 of x. So this is a topological constant. Okay, and then we take the obvious definition that omega is a cscK metric, constant scalar curvature Kähler. If s of omega, the scalar curvature, is equal to s hash, is constant. So the condition is that the scalar curvature is constant. This is a topological constant, which we denote by s hash. And in this case, because I'm assuming projectivity, the scalar curvature, this average, is actually even a rational number. Okay, so from the point of view of PDE theory, this is some quite complicated PDE. It's fourth order, fully nonlinear, very difficult to solve. It's a scalar PDE by the del bar lemma, so it's a PDE just on a function rather than on tensors. And it's quite surprising, I think, just how strongly this PDE reflects the geometry of the manifold. So it's, yeah, really where the geometry comes from in the field. So I'll just mention some results that explain why cscK metrics are so important and how they actually reflect geometry. So they reflect really very strongly the geometry of the manifold. And these days, actually, there are many different ways in which this is true, but I'll just give the most prominent examples of this. So for example, and actually many people have worked on the following results, so we're not going to write down the names so precisely, but I'll try to mention them orally. So first of all, uniqueness. So the statement is that if you have two different cscK metrics in the same Kähler class, then they're actually related by a biholomorphism of the manifolds. So this is really what it means to be canonical. Like you've got a canonical choice of cscK metrics because they're unique when they exist. So if omega prime in C1 of L are cscK, then there is a G in aught of XL. So this is biholomorphisms of X, which lift to L. So then there is a G in aught of XL with G star omega equals omega prime. So in particular, if the automorphism group is trivial, then cscK metrics are absolutely unique. And this will actually play a very important role in this talk. So it's worth remembering this statement quite precisely. So it's saying that when you have a large automorphism group, there are actually quite a lot of cscK metrics, like a finite dimensional family. Whereas if you have discrete automorphism group, you just have a unique, absolutely unique cscK metric. So in the discrete automorphism group case, this is a result of Donaldson from around 2001. In the general case, it's due to Berman-Bernsen from around 2016, I think, and many other people have worked on these statements. For example, Pando Mubuchi in the Kähler-Einstein case, Chen when the first term class is negative, and many others. The second statement is much more classical, actually. So this concerns the automorphism group of cscK manifolds. So the question is, how can you understand the automorphism group of X in terms of the cscK metric, or through the cscK metric? So the statement is that if omega in C1 of L is cscK, then the isometry group, isom of X omega, is actually a maximal compact subgroup of Auto of XL. So this tells you two things. First of all, you can recover the automorphism group from the isometry group. So the isometry group is really as large as possible, essentially. But it's also telling you that the automorphism group is reductive because it's the complexification of a maximal compact subgroup. That's then important motivationally for the links with geometric invariant theory. So this is due to Matsushima, Lichnerowitz, and Calabi as well, particularly in the extremal case. Okay, the next one I want to mention is the link with stability. So this is something we've heard about in previous weeks. I'm not going to go into anywhere near as much detail as has been done recently, but what I'll just mention for the moment is that if omega in C1 of L is cscK, so you're on a polarized manifold that has a cscK metric, then XL is K polystable. I won't define this, it's not going to play such an important role in the talk, but I'll emphasize that this is a purely algebro-geometric notion. So the cscK condition is some kind of very difficult PDE to understand on a compact Kähler manifold. K-stability is defined purely in terms of the algebraic geometry of the projective variety X. An algebro-geometric notion. Okay, and conjecturally existence is equivalent to stability. So conjecturally, existence of cscK metrics is really equivalent to K-stability or K-polystability. And there's been a lot of progress on this in recent years, particularly in the case where the line bundle L that you choose is the anti-canonical class, so you're on a Fano manifold. In that case, the cscK condition reduces to the Kähler-Einstein condition. Then Tian and Bierman proved that Kähler-Einstein implies K-polystability, and Chen, Donaldson, Sun proved the converse, namely K-polystability implies Kähler-Einstein. And then there's been a lot of progress also in the general case from Lee in one direction. And in the other direction, the sharpest result is Bierman, Darvash, Liu, who proves what I've written. But then there were prior results by Donaldson, Stoppe, Sekedi. And yeah, again, many people have worked on that story. Okay, and the fourth thing I want to mention is to do with moduli. Somehow this is the algebro-geometric motivation for being interested in the cscK condition or K-stability. So one can form moduli spaces of manifolds, so polarized manifolds, which admit a cscK metric. And here one should fix numerical invariants. So for example, one should fix Hilbert polynomial. So the topological invariants should be fixed. Anyway. So this is a result that's somehow motivated by the link with algebraic geometry, because stability conditions were really invented precisely to construct moduli spaces. And so the conjecture is that K-stability should be the right notion to form moduli spaces of projective varieties. And that's actually a theorem now in the Fano case. So one can form moduli spaces of K-stable Fano varieties. And that's a result of Otaka and Li Wangzhu. And this result, which is really just for smooth projective varieties, because this is a differential geometric result. This is due to Fujiki and Schumacher from around 1990 for polarized manifolds with discrete automorphism group, and then it's a more recent result of me and Philip Naumann in general. Anyway, so to my mind, these are the 4 results that kind of emphasize the geometric importance of cscK metrics, why one should be interested in them, and, well, if you find yourself in another situation, these are the most important questions one can ask. That link with geometry, at least, there are more analytic questions that one can ask that are very important as well, but these are, I think, the geometric questions. So now I'll turn to the situation I'll be interested in today. So this is holomorphic submersions. So one should think of this, instead of an actual polarized manifold, you have a family of polarized manifolds. And I should emphasize that this is, from now on, all joint work with Lars Sektnan, who's a postdoc in Denmark. Okay, so the setup will require a little bit more notation. So we let pi from xh to bl. So I'll explain the notation. So we'll let this be a polarized submersion. So what I mean by this is the following. So first of all, the morphism pi is really just a morphism from x to b between smooth projective varieties. So this is a holomorphic submersion. Between smooth projective varieties or projective manifolds. So the holomorphic submersion thing, in particular, it means that all of the fibres are complex manifolds. So you really think of this as a family of complex manifolds parameterized by B. So I mean, the technical definition of a submersion just means that d pi is surjective, but it implies that all of the fibres are complex manifolds. So you think of this really as a family of complex manifolds. In particular, this will be a flat family in the sense of algebraic geometry. So this implies that all fibres are complex manifolds of the same dimension. And it implies much more than this, but this is one basic fact that it implies. And this is locally trivial in the smooth category. So if you forget the complex structure, this is locally trivial by a result of Erisman. So just in the smooth category, but actually in the holomorphic category, much more interesting things can happen. The holomorphic structure can genuinely vary in the fibers, giving you variation in moduli, basically. So, but holomorphic structure really can vary. So this is why you think of it as a family of complex manifolds being parameterized by B. Okay, so all I require on the line bundles is that, first of all, h sub b, which I'll denote h restricted to xb, where in turn xb is pi inverse of b. So I'll require that hb is ample for all b and b. So this is the definition of what it means to be a relatively ample line bundle. Relative ampleness just means ampleness on the fibers. So in turn, this means that C1 of H is a Kähler class when restricted to each fiber. So it's a relatively Kähler class. I require then that L is ample on B. And I don't require anything further at all. So I mean, I'm not asking for any relationship whatsoever between H and L apart from this. I mean, there's no relationship between them, just L is ample and H is relatively ample. Okay, So this is the geometric situation I'm interested in, and the question, I now only have a relatively Kähler class, not a Kähler class. So the question is, what does it mean for some relatively Kähler metric omega x? So this is relatively Kähler, it's Kähler on each fiber. So what does it mean for omega x to be a canonical relatively Kähler metric? So I should emphasize that really the point of this is that you want some way to geometrically understand holomorphic emissions in terms of Kähler geometry, just like in the results I explained before, you're able to really understand the geometry of polarized manifolds using cscK metrics. So rather than a representative which reflects the geometry of the manifold, this should be something that reflects the geometry of the submersion rather than the manifold itself. So this should be really reflecting the fact that we have a holomorphic submersion, this relatively Kähler class. Okay, so I'll give some examples where I think one can quite straightforwardly guess the correct answer. That will motivate the definition that we give in the general case. So the first case is if OT of XB HB, so this is the fiber over B and B of the morphism pi. So if this is trivial, for all B and B, then by Berman-Brinson or Donaldson, what you get is that a cscK metric is actually absolutely unique in the Kähler class HB. Typically, one gets uniqueness up to automorphisms, which is like a finite dimensional condition. This is absolute uniqueness when the automorphism group is trivial. So a cscK metric is absolutely unique on each fiber. So in particular, in this case, one can ask for some omega x in C1 of H such that its restriction, so I'll write this as omega b, which is omega x restricted to xb, such that its restriction is cscK for all b and b. And one gets a uniqueness statement. Such an omega x is precisely unique up to pullback from b. So this is unique up to pullback from b. Okay, so the second situation I think geometrically is much more interesting and extremely heavily studied. So if x is equal to P of E, where E over B is a holomorphic vector bundle, okay, so you have a holomorphic vector bundle. I can projectivize it, so I get a projective space in each fiber over B. And I take H to be O of 1. So this is a line bundle that restricts the O of 1 line bundle on projective space on each fiber. So the fibers of this holomorphic submersion are all projective space. Then any Hermitian metric whatsoever H on E, this actually induces a relatively Kähler metric, omega P of E alternative, in C1 of O P of E of 1. I mean, really, you should think about this as, first of all, inducing a Hermitian metric on the O of 1 line bundle and then taking the curvature. There are many ways to understand this construction. The one I think that's most intuitive is that if you remember the construction of the Fubini-Studi metric, really it depends on a choice on inner product on the overlying vector space. And a Hermitian metric is precisely that data. You get an inner product on the vector space. More formally, you can think of O of -1 as a subbundle of the pullback of E to P of E, and then it's just the induced metric from that construction. Really, what's important though is that this omega P of E, this restricts to a Fubini-Studi metric on each fiber. Okay, and this is the really important point about uniqueness. It's what I've just said, essentially, that the Fubini-Studi metric is not actually unique. It's only unique up to automorphisms of projective space. Nevertheless, the Fubini-Studi metric is something that actually fits into the story we've been telling so far, namely this Fubini-Studi metric is actually a cscK metric itself. So what do we really have? We have a massive collection of Hermitian metrics on a holomorphic vector bundle. Each Hermitian metric induces a relatively Kähler metric that's cscK on each fiber. Nevertheless, there's a massive collection then of relatively Kähler metrics that are cscK on each fiber. This is very different to the previous situation when the automorphism group is discrete on each fiber. But it's hinting somehow that the two situations are less different than they appear at first glance, because you still have a relatively Kähler metric that's cscK on each fiber. Just clearly you need to impose some further condition on the relatively cscK metric to actually get it to reflect the geometry of the holomorphic immersion. And actually in vector bundle worlds, this is already understood. Oh, sorry. In vector bundle worlds, this is the Hitchin-Kobayashi correspondence. How do you actually understand this story? This is an extremely important story, but from the 1980s, so fairly classical. So canonical choice. The question somehow for projective bundles becomes, how do you pick a canonical choice of Hermitian metric? And this is a very well understood story. So a canonical choice of Hermitian metric is given by a Hermite-Einstein metric which, and now a new feature is that we have to fix a Kähler metric on B, which for omega B in C1 of L, Kähler, this is really something we didn't see before, that in order to understand the geometry of the vector bundle, you need to fix a Kähler class on the base. And then the condition just becomes that the contraction with respect to omega B of the curvature of the Hermitian metric is a constant multiple of the identity. So the curvature is a two-form with values in end E. This is the identity endomorphism, and the contraction allows you to compare these. These are both sections of the endomorphism bundle of B. So FH is the curvature of the Chern connection associated to the Hermitian metric. Okay, and then the point is that a Hermite-Einstein metric in particular induces a canonical choice of relatively Kähler metric that's cscK on each fiber. So a Hermite-Einstein metric induces a canonical relatively Kähler metric on P of E, which is cscK on each fiber. So what we'd like to understand is what happens for much more general submersions. And I think actually you see that the story was already very interesting for projective bundles. The story of the Hitchin-Kobayashi correspondence established by Donaldson, Willenbeck-Yau played a really important role in complex geometry, especially in the 1980s. And then, it pushed on into applications of gauge theory and so on to four-dimensional topology. And it's really a very rich theory. From my own point of view, I kind of grew up as an algebraic geometer, and case stability, constant scalar curvature metrics, they remain extremely mysterious in higher dimensions. And somehow, from my point of view, the point is that complex manifolds or smooth projective varieties are still very mysterious in higher dimensions. There are very, very few constructions of projective varieties in higher dimensions. It's kind of surprising. Like there should be lots of constructions, but there are actually only a handful. And this kind of holomorphic submersion or fibrations more generally, this is a very important class of higher dimensional variety. And somehow through the minimal model program of birational geometry, this is how you should understand all higher dimensional varieties. So if we were able to understand this sort of question, I think this would give you a real insight into the geometry of higher dimensional varieties. Whereas as it stands, we're able to understand really very little. I mean, we haven't gone further than projective bundles, basically, beyond, well, in this style of construction. There are other things like blow-ups and finite covers, and of course the Calabi-Yau general type Fano cases. But I think a real problem in our understanding in higher dimensions is not understanding fibrations, because they play such an important role in higher dimensional algebraic geometry and hence scalar geometry. Anyway, so this was the setup and the question. I'm now going to tell you the answers. We have developed a notion of what it means to be a canonical relatively Kähler metric in this situation. These are what we call optimal symplectic connections. So this is still a relatively new notion. The paper formulating this condition went on the archive just about a year ago, sometime July last year. We've been trying to establish results concerning how these connections, these relatively Kähler metrics actually do reflect the geometry of holomorphic emissions, and that's what I'll explain today. So we're going to start off with something quite similar to the projective bundle case that we saw above. So we let omega x be a relatively Kähler metric. So omega x in C1 of H, so we have the same setup as before, so x to b is a holomorphic immersion. And the key thing that we're going to impose is that it's cscK on each fiber. Okay, and as we saw, when the fibres have automorphisms, there are lots and lots of these. This is an infinite, you can get an infinite dimensional family of such relatively Kähler metrics. Then omega x defines a splitting of the natural short exact sequence involving the tangent bundle that you get for a holomorphic immersion. So a splitting of the short exact sequence 0 to v to tx to h to 0. So v is the vertical tangent bundle, it's the kernel of d pi. So v is the kernel of d pi. And h sub x is defined to be the orthogonal complement of v sub x in the following sense. So h sub x is the set of u in txx such that omega x at x of uv is equal to 0 for all v in vx. So orthogonal with respect to the symplectic structure that we have induced by omega. Okay, and actually this is where the name comes from, symplectic connections. When you construct a connection in the sense of differential topology like this, in symplectic geometry literature, this is when they call omega a symplectic connection. So this is where the name comes from. This in turn defines a splitting on all tensors, not just vector fields. In particular, you can talk about the horizontal component, the purely horizontal component of omega x itself. And I will define this to be mu star fh. So this is the definition of this. So it's the purely horizontal component of omega x. The point is that you can also construct this in another way, which makes it clear that this is the analog of the curvature. So this is the thing that plays the role of the curvature f sub h on a projective bundle. So this is called the symplectic curvature in the symplectic geometry literature. Okay, but we get much more. The geometry is more involved in the projective bundle case, so we'll need more notation. So omega x also defines a metric, because it's positive on the fiber directions, it defines a metric on V, the vertical tangent bundle, and hence its top exterior power, so minus kx over b, the relative canonical class. So this is wedge to the mv, so m will be the dimension of the fibers. And I'll let the curvature of this be denoted by rho. We'll need more. We need a vertical version of the Laplacian operator, so omega x also defines a vertical, meaning fibrewise, Laplacian, Laplace of v. So what this means is you take a function on x, you restrict it to a fiber, compute the Laplacian there, that very smoothly, so you get a smooth function back on the total space. And the interesting function that we can construct from this, which I'll denote by eta, is the vertical Laplacian of the contraction with respect to omega b of mu star fh plus the contraction with respect to omega b of the horizontal component of rho. And okay, we're not going to ask that eta is constant. This is almost the PDE defining the optimal symplectic connection condition, but actually we need to take a projection to make this an elliptic PDE essentially. So we'll define some projection onto some Smalley subspace of functions, which is finite dimensional on each fiber, and that will be our optimal symplectic connection condition. So first of all, we set E sub b, so this is the set of functions which are holomorphic potentials on the fibers. This is a finite dimensional vector subspace of smooth real valued functions on xb. So we set this to be functions phi sub b with, first of all, the integral over the fiber of phi with respect to omega b to the m. This should be 0. So these are functions which integrate to 0 over the fibers. And the condition that's really important is that del bar on b, so this is really a fibrewise condition. So phi b is now a function on the fiber. You can take the gradient with respect to the Riemannian metric induced from omega b. You take the 1, 0 part of that. That's a smooth section of the holomorphic tangent bundle. You can take del bar of that and ask if that's 0. That's saying that that smooth section was actually a holomorphic section. So you get a holomorphic vector field. So these really correspond to holomorphic vector fields on the fiber. This is somehow the geometric point of the story, that you get uniqueness of cscK metrics up to automorphisms of the fiber. This is reflected by precisely this vector space E sub b. So we'll take this projection P, so this is from C infinity of x, takes all smooth functions on x to C infinity sub E of x. So this is essentially the functions which restrict to functions in E sub b for each b and b. So this is the L2 orthogonal projection. So this is just a projection onto a subspace. So here phi is in C infinity E of x. If phi restricted to xb is in EB for all b and b. So one should think of these as corresponding to smooth vector fields on x, which restrict to holomorphic vector fields on each fiber. Okay. And actually, a technical condition that comes in our work for kind of analytic reasons, it's sort of like a smoothness hypothesis, is that we assume that del bar b grad 1b, 0b, we assume that the kernel of this operator has dimension independent of b. So this is really just a technical hypothesis. It's automatically satisfied, for example, when the fibration is locally trivial, which is sort of like an analog of the projective bundle case, but much more general. Okay, so finally we can give the definition, which is going to be playing the most important role. So this is that omega x is an optimal symplectic connection if P of eta, so this is, I'll recall P of vertical Laplacian of the horizontal contraction of mu star FH plus the contraction, the horizontal component of rho, so this curvature of the metric on the relative anti-canonical class, if this is 0. So you take this function, project onto fibrewise holomorphic vector fields and ask that the projection vanishes. Okay, so the condition is quite involved because you have all of these different terms. My first remark that I want to make is that this is really equivalent to the Hermite-Einstein condition on a projective bundle. So this is equivalent, although it's not obvious at first glance. So the Hermite-Einstein condition, when x is equal to P of E. So the argument is not incredibly difficult. The point is that actually this mu star FH, this is on a projective bundle, indeed the quantity you're used to. It's induced by FH, where H is now the Hermitian metric, so the usual curvature of the Chern connection. The contraction is the usual contraction on B. Because we have a kind of relative Fano situation, this rho H becomes equal to mu star FH. So one of the terms kind of equals the other, except you have this vertical Laplacian. But actually what happens is that the vertical Laplacian ends up having this function as an eigenfunction with eigenvalue 1 even. So this really just reduces to the Hermite-Einstein condition because you get a condition that's like P of the contraction of F is 0. But actually in this case, again, because of some kind of equivariance reason, this projection is just projection orthogonal to the constant. So it's really just asking that the contraction of F is a constant multiple of the identity endomorphism. Anyway, okay, so the argument involves a little bit of work. In general, it seems to me that the problem should kind of interpolate the difficulty of the cscK problem with the Hermite-Einstein problem. So in general, the problem seems to me, it seems closer to the vector bundle theory than the manifolds theory. In many ways, I mean, I think the geometric considerations are more similar, but also it seems easier than the cscK problem to me, but harder than the Hermite-Einstein problem. But it has the same kind of flavor as the Hermite-Einstein problem, I think. So I'm kind of optimistic that a lot of work can be done on this problem. It won't be quite as difficult as the cscK problem. But I mean, somehow, even suppose it was as difficult as the cscK problem, that would be fine because there's been so much progress on that problem that seemed previously quite intractable. Okay, so anyway, the condition does generalize the Hermite-Einstein condition, but it somehow, at least at the moment, seems like it comes out of nowhere. And when we wrote this paper about a year ago, we were also quite confused as to what the geometric significance of this quantity was. We really wanted to be able to prove some kind of definitive results relating this condition to geometry. So we were actually able to do this. So these are all all joint work with Lars Sektnan. I'll just write down his name for the first such theorem. But okay, so let's aught of pi denote the G in aught of XL, which preserve the fibres. So pi composed with G is equal to pi. So pi is the projection coming in the definition of the holomorphic submersion. So this is the natural automorphism group of the holomorphic submersion pi. And the isometry group of omega x with respect to pi, this is equal to the G. Now actually I'll do a slightly cheating thing and I'll just let it be a subgroup of aught of pi such that G star omega x is equal to omega x. The point is that omega x isn't actually a Riemannian metric. It's only like it only induces something positive on the fiber directions. So this is kind of the quickest and easiest definition of what it means to be the isometry group of something that's only relatively positive. Anyway, this is just notation. These are the natural isometry groups and automorphism groups. Then our result says that the isometry group of omega x pi, this is a maximal compact subgroup of aught of pi. So in particular, aught of pi is reductive. So you can really understand the automorphism group of a holomorphic submersion through understanding the isometry group of an optimal symplectic connection. These actually do represent the automorphism groups of holomorphic submersions. Our second result concerns the link with algebraic geometry. So if a submersion, a holomorphic submersion, admits an optimal symplectic connection, then this implies a notion of algebro-geometric stability. So then it is semi-stable in a purely algebro-geometric sense. This is probably a good point to mention that this is really the only result in the talk that relies on projectivity. Everything else would have worked for compact Kähler manifolds. And we expect that this result would still be true in the compact Kähler setting, but we don't know how to prove it. I won't get into this result really at all, but I'll just advertise that I'm giving this Zoom algebraic geometry seminar on Thursday. This will be the same sort of material that I've covered today, but kind of orthogonal in motivation. It'll be really motivated by the algebraic geometry rather than the differential geometry. And the whole talk will be essentially explaining the algebro-geometric counterpart, in particular, what our notion of stability is for a holomorphic submersion, and maybe a few words about how we actually prove this result. So the one that we really don't have is the construction of moduli. So our conjecture is that one should be able to form moduli spaces of holomorphic submersions admitting an optimal symplectic connection over a fixed space, so over BL fixed. So you should think about this like a very classical statement from the 80s that one can form moduli spaces of stable vector bundles. It's like slope stable vector bundles. In particular, one can form moduli spaces of vector bundles which admit a Hermite-Einstein metric. We've seen that that's a special case of an optimal symplectic connection. So this is sort of like a conjecture that says, if you're interested in the geometry of holomorphic submersions that aren't just projective bundles, which is a very important problem, I think, in algebraic geometry, this is the notion of stability that you should impose. So this is the right kind of approach to studying moduli spaces of submersions over a fixed space. And the last result, which is the one that I'll spend the next 10 minutes kind of explaining parts of the proof of, concerns uniqueness. So if we have two different optimal symplectic connections, omega x prime in C1 of H, so if these are both optimal symplectic connections, then there exists a G in alt of pi with G star omega x is equal to omega x prime. Okay, but now there's a difference because even when the fibres have discrete automorphism group, a fibrewise cscK metric is not absolutely unique. It's only unique up to pullback from the base. So what you get is that this is equal to plus I delta bar pi star phi b, where phi b is in C infinity of b. So you get uniqueness up to automorphisms and up to pullback from the base. So this is really the kind of best possible uniqueness statement for optimal symplectic connections. So this is the result that I want to explain for the next 10 minutes. All of these results generalize quite classical results for vector bundles in particular, because the optimal symplectic connection condition really is the Hermite-Einstein condition on the projective bundle. So for example, the uniqueness is a result of Donaldson for vector bundles. He proved that Hermite-Einstein metrics are unique, and this recovers his proof, but with a completely different method, much closer to kind of modern Kähler geometry than Donaldson's approach from the mid-80s. Okay, so anyway, this is this uniqueness result. This is the one I want to give a sketch of the proof of. Okay, and I'll just assume that we're in the technically much simpler case that the automorphism group of pi is actually discrete. So we assume that aut of pi is even trivial. I'll say a couple of words at the end about how you remove this assumption. Okay, so a little bit of background that we need is we have x over b. So this is actually a family of complex manifolds where the fibres admit cscK metric. So xb, hb admits a cscK metric. For all b and b. So in particular, this gives you a morphism Q from B to the moduli space of manifolds that admit a cscK metric that I mentioned earlier in the talk. So M itself has a Kähler metric. So this is something we also prove. And again, is due to Fujita Schumacher in the technically simpler case of discrete automorphism group. But M is a Kähler metric, omega WP. So this is the Weil-Petersson metric. So in particular, Q star omega WP is semi-positive. So this is some semi-positive form on B that reflects the variation of the fibres in moduli. So the first step, step one, which is a variation of a result of Yoshi Hashimoto and Yu Zhang. So they don't prove exactly what I mentioned, but the proof that we gave for this statement is essentially the same as their proof. So we find alpha, a Kähler metric on B, such that, so here omega B is fixed. Such that the scalar curvature of omega B minus the contraction with respect to omega B of Q star omega WP plus alpha is equal to a constant. So this makes omega B so-called twisted cscK metric. So this PD is the twisted cscK equation. This is really a kind of technical result. The point is that omega B is completely arbitrary here, and we don't want to make any hypotheses whatsoever about omega B. This allows us to think of omega B as a canonical metric of its own, because there's a lot of geometry behind twisted cscK metrics that allow you to think of them as canonical metrics. And that gives us a kind of new toolbox in order to complete the further steps. This is kind of like a technical trick. Step 2, and this is really the content, so this is the hardest one. And in particular, this uses that omega x as an optimal symplectic connection. So we consider for k a large integer, k omega b plus omega x. So for k very large, this is Kähler. Then the first thing we show is that there exists a function phi r in C infinity of x, such that the scalar curvature of k omega b plus omega x minus the contraction with respect to the same thing, k omega b plus omega x. Oh, sorry, plus, I've forgotten to use the function phi r, plus k inverse I del bar phi r minus the contraction with respect to the same thing, k omega b plus omega x plus k inverse I del bar phi r. And now just alpha, or really rather the pullback of alpha to x, is equal to O of k to the minus 2. So this is saying that actually you can, at least after this using this function phi r, using the fact that omega x is an optimal symplectic connection, this gives you a good approximation to a twisted cscK metric on the total space X itself. We continue inductively, so we find omega kr, which is k omega b plus omega x plus k inverse phi 1, which is phi r plus some other terms, plus k to the minus 2, phi 2, plus dot dot dot, with the scalar curvature of omega kr minus the contraction with respect to omega kr, alpha, or the pullback of alpha to x, minus some constants, is equal to O of k to the minus r minus 1 for all r. So you give me an r and I can find you very close approximations to genuine twisted cscK metrics on the total space X itself. And then we perturb. To say omega k hat, a genuine twisted cscK metric on X itself. Now we're in a good situation because there are already uniqueness results for twisted cscK metrics. So this is step 3, just the final step. So by Kähler, in this case, or Biermann-Bernstein in complete generality, essentially. Twisted cscK metrics with alpha fixed, twisted cscK metrics are unique. So that tells you if omega x prime is also an optimal symplectic connection, then, okay, you could follow the same strategy. Then you would get some resulting omega hat k prime, sorry for the notation, but this would actually equal omega k hat. But then these genuine twisted cscK metrics were really just small perturbations of the approximate solutions we constructed. So this tells you that the approximate solutions, so we argue really that the approximate solutions omega kr and omega k or prime are actually equal, essentially by some kind of variant of the implicit function theorem. This allows us then to include that omega x is equal to omega x prime. So this is how we conclude uniqueness of optimal symplectic connections. We perturb to genuine twisted cscK metrics on the total space of the submersion, apply uniqueness of twisted cscK metrics, and then try to show that this actually implies uniqueness of the approximate solutions that we use. So this gives uniqueness, and I'll just mention that in general, so my big hypothesis here was that actually the automorphism group of the submersion is actually discrete. In general, auto pi case, so we use the same strategy as above. but we can't conclude that they're actually equal. We only get that one is in the closure of the orbit of the other with respect to the automorphism group action. But then there are actually some ideas of Darvash and Rubinstein from their kind of breakthrough paper on coercivity of the Mabuchi functional that apply to the situation. So we use some ideas of Darvash Rubinstein. Okay. And again, this involves a kind of deeper understanding. The general case involves a deeper understanding of the structure of the automorphism group of submersions, but we'd already established those results. And anyway, thanks. That's the end of the talk.
Thank you very much for the talk. And now it's time for questions and remarks. Actually, I have a question. Since our the motivation of introducing these kind of notions are to construct the moduli space, so I'm just wondering if you have a corresponding notion in the singular case, if your family has a singular fibers.
Yeah, that's a really good question, and I think that's something very important to understand. So the answer is basically no. Even when the fibres have discrete automorphism group, it's not so clear to me exactly what the right condition is on the fibrewise cscK metrics. I mean, are you considering absolutely arbitrary families in your situation, or something more constricted? Yeah, it's a good question. I would really like to be able to prove these sorts of results when the fibres have singularities. Actually, this would allow you to produce a lot more examples as well, because typically in higher dimensions, fibrations have singular fibres. From the point of view of moduli, this is not such a big problem necessarily, in the sense that at least the way we think about it, like the motivation for the moduli really comes from the algebraic geometry. Our notion of stability for fibration doesn't make any hypotheses on singular fibres or anything like that. That makes sense in complete generality. But it would be really good to have a notion of what an optimal symplectic connection is on an arbitrary fibration, and not just holomorphic submersions. But that's not something we know how to do.
Okay, thanks. Some other questions or remarks? Okay, there seems to be no more questions. So thank you very much for the talk, and that's the end.
Thanks.